Hey everyone, welcome back to the channel. In this episode I'm going to go over some of the design decisions that I've made and all of the research that I've done so that I know which electrical components I'm going to use for this project. Okay, so first off I want to cover some of the battery information that I have come across. I have come across quite a few different battery designs that I wanted to try to use, and I ended up going with something totally different altogether, but we'll start with the example that we have in the Excel sheet right now. In this Excel sheet right now we have a battery info link from battery hookup with a bunch of Samsung batteries. Now unfortunately I waited too long to make this video since I found this link, so this link no longer works, but the batteries that they have are typically the same. So they'll have a nominal battery voltage of 3.6 volts. This battery in particular had 3.1 amp hours. And my desired battery capacity using these batteries was 150 amp hours. This is like a configurable number that we can use in some calculations later on. But for now, for the sake of being easy, I just set this number to be arbitrary to be usable on a vehicle application. Finally, we also have the number of dollars that these batteries cost in 200 battery quantities, which comes down to a certain amount of money per cell. So next, what we want to do is we want to decide how many batteries do we need given that these batteries are at these specifications. Two things to consider. One, I want to make sure that I have enough amp hours for me to be able to use to make the vehicle usable for a certain period of time. Second, I want to be able to design the entire battery pack as a whole to be able to power my motor. The motor that I chose is from Thunderstruck EVs. They're an American company that sells a motor called the ME1507. And in that link and in some of these pictures down below, we can see some more information about it. But all this information in orange is important information that I need to set in order to do some calculations to make sure that I designed everything properly. So first we have the continuous power of 10 kilowatts, so we want to be able to design a battery that can provide that if the motor is asking that. Second, we have the continuous current, which again, we want to make sure that it can provide that continuously, but also be able to manage a certain peak current that the motor is capable of using. So if the motor is asking for more amperage than the batteries can provide, I have a problem. So I want to make sure that I use a certain number of batteries to prevent that from happening, or maybe I set something in the controller to keep the peak current forever being reached because the batteries will never want to provide that much. And there's a couple of other things that you can do as well. Another important thing about the motor is the RPM, the max RPM. I need to know what speed the motor is running because I need to be able to convert that into a wheel speed. I could be running at 10,000 RPMs, but I could have a tiny diameter, and by the time that I set up all my gear ratios to turn a wheel, it ends up not being usable. So I have to take this speed into account and then do some gear ratio changes if I need to down here below to be able to make the vehicle go the speed that I want it to go. But we'll get to that later. So going back to the batteries, we have capacity adds in parallel and voltage adds in series. This is very important when using tiny little AA looking batteries. Now they're not actually AA, they're 18650. This regardless is important for combining these batteries in parallel and in series to get the capacity and the voltage that you want for your system. So originally, I wanted to make this system 100 volts because that is what the motor is capable of operating at to get its full RPM range. So if I go over here, I say, okay, I have 3.6 volt batteries, and if I want a 100 volt battery, I have to add them in series like I have here on the Excel sheet. So 100 volts target divided by 3.6 volts per battery gets me a total of 27 batteries in series in order to get me to my operating voltage. Now I have 27 18, 16, 50 batteries in series, but that's not going to last at all. They're 3.1 amp hours. I'm going to turn the motor once. I'm going to pull the throttle one time, and by then all the batteries will be dead because it's asking for so much at once. So what I need to do is I need to increase my capacity by adding more of those 27 series batteries than in parallel, so that I have this giant mesh of batteries that are capable of providing both the voltage and the capacity that I need. So to do that math, I have 3.1 amp hours, but I want a target battery capacity as a whole pack to be 150. So I just take this 150 divided by 31, and that gets me to a 49. And in both of these calculations, I have a ceiling operator applied because I can't have a portion of a battery. I also have a couple of other calculations down here to determine like how much money am I getting per watt hour so I can be efficient with my energy costs, but I'm not really going to cover that, but the math is here if you guys want to look at it and double check. So there are 181650 batteries in this example. The beautiful thing about some of these batteries is that the number that's associated with the battery name is indicative of the geometric measurements. So 650 rather, that means that the battery is 18 millimeters in diameter and 65.0 millimeters in length. And there are also other similar cylindrical batteries like the 21700 batteries, which are, just like the 18650s, 21 millimeters in diameter and 70.0 millimeters in length. And knowing that, I can do a bunch of volume calculations to make sure that I have enough space under my bike. Luckily, I had a buddy come by and do a photogrammetry scan using a newer iPhone. Apparently they can do that nowadays. It's pretty cool. And I was able to kind of mock up how much space I have and do all that in CAD. And this is very informational because it shows me how much battery I can fit in certain areas of the bike. But in reality, I ended up scrapping all of these different types of battery designs simply because of the amount of manual labor to put all of these batteries in series and in parallel. With these tiny little batteries, you have to get a lot of nickel tin strip, you have to do a lot of spot welding, and a lot of manual assembly of the batteries themselves. So what I did instead is I actually went on to AliExpress and I found these batteries here. These are Litokala batteries, and they operate just like the other ones do, except these ones are nice in that they have a significantly higher amp hour value. So these ones are 202 amp hours. And like I had said in my Excel sheet, I have 150 amp hours that I was hoping to go for, but these ones are 202 out of the box. So if I have 202 amp hours, but the battery is 3.2 volts, all I need to do is add them up in series, and then I have a battery that can meet the design specifications for my bike. Now, the one thing I do sacrifice in doing this, though, to keep down the cost, is I actually have to move from a 96 to 100 volt system to a 72 volt system. So instead of buying 100 divided by 3.2, which is equal to like 30 batteries, I switched down to a 72 volt, so I did 72 divided by 3.2, which got me about 23 batteries in parallel instead. So for this project, to keep costs low, to keep things simpler and not as deadly, I decided to go with 72 volts, but with how big my bike is, I can add extra batteries on the outsides of the bike to make the voltage of the battery pack higher if I wanted to in the future. So moving on to gearing. So there is a wheel on the back of the motor and it's connected to a drive shaft. And I need to know how much I need to spin the drive shaft in order to turn the wheel. So it looks like from my previous video and counting it that I have a ratio of 3.8 input turns equates to 1 output turn. So that means that I need my input shaft to spin faster than the output in order for it to operate at a usable speed. And then next, after that, knowing that my max motor speed is 5,000 RPM, I can do a little bit of math to find out what the actual output speed is of the motorcycle. So if I have So it's all this math here. You guys can look over that. But basically, I'm taking into account the gear ratio. I have an extra spot here on line 20 that allows me to add an optional ratio from motor to a intermediary gear so that I can step up or step down to have the output speed be faster or slower. So if I decrease this motor to shaft ratio to like 0.75, you'll see that my max speed goes up to 66, for example, to 88. So if I added an extra tiny little gearbox to connect to the input shaft of the motorcycle's drivetrain, I can go faster with the motorcycle if I wanted to. And I designed a bunch of other things for this 0.75 motor to shaft ratio over here. And I have a bunch of items picked out from McMaster Car. I designed which chains I should use for which sprockets and how far away they should be. There's a lot of calculators out there that you can use to find out how far away two sprockets need to be in order for a chain to connect to them properly. But again, you always need a tensioner, and they need to be enclosed to make sure that the moving parts are safe from being pinch points or areas of the motorcycle that could cause bodily harm. The last thing I wanted to cover in this video is some of the stuff that I bought. I'm not going to go over all of it, just because we'll get into the implementation later. But like I said, here are the batteries that I bought. I bought a pack of 8 and then a pack of 16, which got me 24, so I actually have one battery left over. My total cost is $97.70 per battery, with a battery that will eventually be 14.8 kilowatt hours, which would actually end up costing me $158 per kilowatt hour, roughly. But a little bit more expensive, got me a little bit lower voltage than I would have wanted, but it saves me so much manual labor, so much time checking battery voltages and binning them all together and welding them together and wrapping everything 3 times over. So I think I'll spend a little bit of the extra money to make it easier to implement, and for now, make my bike a 72 volt system and add later if I needed to. 2 more things I want to cover, just because they're so relevant to the battery, are the BMS and the actual charger itself. So this is the BMS, which stands for Battery Management System. I need to monitor the voltage of every single battery individually, which is another reason why a 72 volt system would work better, because I have fewer batteries in parallel that are connected together that I need to manage. This BMS measures from 17 to 24. The 17S, 24S, that is the number of batteries in series. So I bought this one that you see on the screen with this current configuration. So it's a 24 series battery, 60 amp BMS with UART and Bluetooth connectivity, blah, blah, blah. But I bought this one because it specifically has enough battery voltage monitoring wires to satisfy what I need for the battery pack that I plan on designing. So this has 24 monitoring wires, and I have 23 batteries. Cool, I get 1 left over. Now, if I want to upgrade my battery system to 100 volts, then I have to buy a different BMS. And luckily for me, I actually forgot to change my BMS when I decided to change how I wanted to design my battery. So I do have that BMS that is going to sit in my garage and cost me $200 that I didn't need to spend. But anyway, I can upgrade now if I need to. Or I could sell it on some sort of marketplace, or a certain list owned by a man that starts with a C. But either way, this connects to the battery and it connects to the charger so that I can monitor my voltages of all of my batteries and make sure that they're all balanced when it gets charged. Second is the charger. So similar to the BMS, it is also rated for 72 volts, and there's a bunch of different other amperage configurations that you can purchase. There are these 5 different ones. I bought the 72 volt 8 amp system. This is listed as 84 for some reason. Well, anyway, This is a battery charger that charges up to 84 volts, and I chose the one that was 8 amps, and it's not listed on here. But I purchased this one. With this, basically the output amperage determines how quickly the battery will charge. So if I have a 202 amp hour system and I have a charger that's providing 8 amps, I just take the 202 divided by 8 amps, which is outputting from this charger. That gives me like 25-ish hours to charge. And then you have to factor in a little bit of energy transfer inefficiency, so it might take a little bit more than that. Fortunately, I don't ride motorcycles that much, so if it has to sit and wait for a day for me to charge it, then I guess it's not too big of a deal. So, you know, it's just to save some money and to make things stay a little bit lower on the cost side. So I went with this. So that's everything regarding the batteries, the charging system to be able to charge it. And then in future videos, I'll go over how I do the small accessories, so everything on the 12-volt side. So that's all I wanted to cover for today. Thank you guys so much for watching. I hope to release some videos about redoing the front fork and cleaning up the frame in the near future. So until then, I will see you guys in the next one.